Something ate a 9-foot great white shark and drove 2,000 feet straight to the bottom of the ocean. Not a whale, not a sea monster. Something the scientists in the room had no category for. And the only reason any of us know it happened at all is because a small plastic device washed up on a beach 4 months later, carrying the entire record of the event inside it. 2 numbers. That is all it took. 2 numbers on a screen. And a room full of marine biologists went completely silent. That was 2003. And what those 2 numbers eventually forced science to admit changed everything we thought we knew about what sits at the top of the ocean's food chain. Here is exactly what happened. November 2003, the southwestern coast of Australia. A research team is running the first large-scale great white shark tagging project those waters have ever seen. Filmmaker Dave Riggs is there to document it. The goal is simple. Attach data loggers to healthy great whites, track their movements, learn where they go, how deep they dive, how they use the coastline across the seasons. Routine scientific work. Important, but routine. One morning they pull up alongside a 9-foot female, roughly 500 pounds. Healthy, confident, moving through the water with the easy authority of an animal that has never once had reason to look over its shoulder. Someone on the crew starts calling her Alpha. The name stays. The device they attach to her is a data logger. Small, rugged, designed to do one job silently for months at a time without broadcasting a single signal. It records depth, it records the temperature of the water surrounding the shark, it captures light levels and movement at regular intervals, it stores all of it internally without telling anyone anything. Then on a preset date, it detaches from the shark, floats to the surface, and transmits everything it recorded to a satellite. Scientists can then reconstruct exactly where the animal went and what it experienced, provided the animal is still wearing the device when it releases. That last part matters, because the device does not know the difference between a living shark wearing it and a dead shark wearing it, or a device sitting inside the stomach of something that swallowed the shark whole. 4 months after tagging, the device does not surface via satellite first. It washes up physically on a beach, roughly 2.5 miles from where it was originally attached. A beachcomber finds it. The data is recovered. The team loads the numbers onto a screen. In the room is expecting the ordinary. Slow cruising patterns, temperature drifting gradually with depth, the wide, unhurried loops of a large shark moving through familiar coastal territory. That is what these deployments normally show. That is not what the data says. The tag shows a plunge, not a gradual dive. A sudden vertical drop to nearly 1,900 feet, accomplished in minutes, and then the temperature reading does something that stops the entire room cold. The surrounding water at 1,900 feet off the Australian coast is approximately 46 degrees Fahrenheit. Cold, genuinely frigid. If the tag had simply detached and sunk on its own, or if Alpha had died and drifted down with the device still attached, 46 degrees is exactly what you would expect the reading to show. That is not what it shows. Heat temperature goes up. It climbs from 46 degrees to a sustained 78 degrees Fahrenheit, a jump of more than 30 degrees. And it does not spike briefly the way a malfunctioning sensor might. It holds, stable, 78 degrees, nearly 2,000 feet down in water that should be close to freezing. Riggs has described reading and rereading that data, unable to accept what the numbers were telling him. But the numbers would not change, because there is essentially one explanation for a warm, stable 78-degree reading at extreme depth in frigid open ocean. A tag does not log that unless it is no longer in the ocean. It was inside something alive, something with a warm interior that had swallowed Alpha, tag and all, and then carried her downward with the meal still inside. Picture that the way Riggs had to in that room. Something out there swallowed a 500-pound great white shark whole, descended nearly 2,000 feet into the dark, and then simply carried on. And not one person at the surface saw a thing. No fin, no disturbance, no photograph, no witness of any kind. The only reason any of us know this happened at all is that a piece of plastic washed onto a beach 4 months later carrying the receipt. Before getting to what the team eventually concluded, you need to understand exactly what kind of animal Alpha was. Because most people carry some vague sense that great whites are dangerous without fully considering what that actually means. A great white shark is not simply a large fish with efficient teeth. It is the product of more than 400 million years of evolutionary pressure, refined by the ocean into something that operates at the outer edge of what biology allows. The largest confirmed individuals exceed 20 feet in length and weigh more than 5,000 pounds. Their sensory systems can detect a single drop of blood diluted across enormous volumes of water. Tiny organs clustered in the snout, called ampullae of Lorenzini, can register the electrical pulse of a heartbeat buried in sand from considerable distance. In short bursts, they can close on prey faster than a human nervous system can process the threat. Their teeth are serrated, endlessly replaced, stacked in rows so that when one breaks or wears down, the next simply rotates forward into position. This is the ocean's most refined hunting instrument, an animal that can smell a wound across open water, feel a heartbeat through solid seafloor, and cover distance faster than instinct can respond to. But here is the part that matters most for this story. Being an apex predator is not about size or speed alone, it is about position. The definition of an apex predator is an animal that nothing hunts. Everything below it in the food chain organizes its entire existence around avoiding it. And above it, there's nothing. That is what apex means, the ceiling. For as long as marine science had been studying great whites, that was the operating assumption. Alpha was the ceiling. She was the thing other things ran from. She had never once in her life needed to run from anything, which is precisely why nobody in that room wanted to say out loud what her tag was telling them. The team worked through every candidate the ocean could offer and watched the theories collapse one by one. First suspect, the orca. Orcas can kill great whites. Off South Africa, orcas have developed a predation technique that is almost clinical. They flip a shark onto its back to induce a paralytic trance called tonic immobility, then open the body cavity and extract the liver with extraordinary precision. It is efficient. It is well documented. An orca gut containing warm prey and a swallow of cold seawater could plausibly produce a temperature reading in the range of what Alpha's tag recorded. But the depth killed the orca theory. Orcas are not deep divers by nature. They hunt near the surface. Even the most extreme documented orca dives fall well short of 1,900 feet. An orca does not casually drag prey to that depth and linger there for an extended period. The diving behavior simply does not match the physiology. The orca stayed on the board as a suspect, but slid down it considerably. Second suspect, the sperm whale. Here's an animal that genuinely lives in the deep ocean. Sperm whales pursue squid to depths of several thousand feet, far deeper than Alpha ever went. The largest males stretch past 60 feet in length and weigh more than 100,000 pounds. A sperm whale's throat could physically accommodate a 9-foot shark without difficulty. On depth alone, no problem. But the temperature worked against it in exactly the opposite direction. Sperm whales are warm-blooded mammals maintaining internal temperatures around 97 to 99 degrees Fahrenheit. 78 degrees is far too cool for the inside of a sperm whale under any conditions. And their entire feeding strategy is built around soft-bodied prey in the deep water column, not large surface predators with rough skin and cartilaginous skeletons. Wrong temperature, wrong diet, wrong prey profile. Out. The team then considered other large shark species, a giant tiger shark perhaps, or an oceanic white tip. Both highly aggressive, both opportunistic feeders. A tiger shark in particular will attempt to swallow nearly anything that fits inside its jaws. But neither species grows large enough to take a 9-foot great white whole. The biggest tiger sharks on record reach roughly 14 feet. And to consume a 9-foot shark entirely, you do not need to be slightly larger than your prey. You need to be enormously larger. The proportions simply would not close. There was even a brief stretch where someone proposed a colossal squid, something theoretically large enough to envelop a shark and drag it into the deep. That theory did not survive examination. A cold-blooded invertebrate has no warm interior. Its body temperature is simply the temperature of the surrounding water. There would be no warm cavity for the tag to detect. One by one, every conventional answer burned away. Orca, wrong depth. Sperm whale, wrong temperature, wrong prey profile. Large sharks, not large enough. Squid, cold-blooded. And as that list exhausted itself, the team found themselves facing a possibility that was somehow both completely obvious and almost too uncomfortable to say out loud. What if the animal that ate Alpha was another great white? Not a slightly larger rival that won a territorial confrontation. Not a competitive clash over a carcass that turned fatal. A great white of a size that most marine biologists had never seriously considered putting on the table. A shark so large that a 9-foot, 500-pound great white represented nothing more than a meal. They did not guess their way to that conclusion. They reasoned it, and the key to the reasoning was temperature. Most sharks are cold-blooded. Their internal temperature matches the surrounding water, but great whites are not most sharks. They belong to the mackerel shark family and carry a rare physiological adaptation called regional endothermy. Using a specialized network of blood vessels, known as a countercurrent heat exchange system, they trap and recycle the metabolic heat generated by their own muscles. This keeps their core temperature, their eyes, their brain, and their digestive system meaningfully warmer than the water around them. It is the adaptation that keeps them fast and lethal even in cold ocean conditions. An average great white stomach might run somewhere around 65 to 70 degrees Fahrenheit. In deep, frigid water, even that might be generous for a mid-sized animal, but 78 degrees is warmer than a typical mid-sized great white would produce. A significantly larger great white changes the entire equation. More body mass means more muscle tissue. More muscle means more metabolic heat generated. More overall mass means that heat is retained far more effectively against the cold pressing in from the outside. Inside the gut of a truly enormous great white, a stable 78-degree reading is not a contradiction. It is exactly what the physics would predict. The reading that had initially looked like a glitch suddenly pointed at a single kind of animal. The depth fit as well. Once researchers let go of the assumption that great whites stay exclusively in shallow coastal water, the picture clarified. Great whites have been tracked by other tagging programs diving past 3,000 feet in open ocean. The 1,900 feet that Alpha's tag recorded is extreme, but it falls within the reach of a very large individual operating at the upper end of the species' diving capability. And that left one final question. How large does a great white need to be to swallow a 9-foot shark whole? Researchers studying this kind of predation estimate the predator needs to be roughly twice the length of the prey. Run that number against what the tag recorded, and you arrive at a predator somewhere around 16 to 17 feet long, weighing more than 2 tons. A shark sitting right at the upper edge of what the species is believed to reach, and perhaps slightly beyond it. If you reconstruct the moment, the picture is brief and merciless. A larger shadow rising from below, the way great whites attack, fast and committed from underneath. A single strike in the half-second before Alpha could respond, and then the long descent into dark water with the meal still inside. The tag did not record the ambush itself. It recorded the aftermath, the plunge, the warmth, the sustained period of digestion at depth. And the aftermath alone is more than enough to reconstruct how it began. Here is where the case stops being arithmetic and starts becoming something genuinely unsettling. The team's conclusion pointed to a female great white of exceptional size. Females of the species grow considerably larger than males across their lifespan. But what about the upper limit? How large can a great white actually get? For decades, the scientific establishment filed away reports from fishermen and naval crews describing great whites of 20 feet or more as exaggeration, stretched memory, the inevitable inflation that happens when a close encounter gets retold over years. But what if those accounts were not exaggerated? What if the ocean holds great whites of a size we have simply never managed to tag, measure, or photograph? Animals living far out in deep open water, away from coastlines, away from vessels, away from the shallow bays where almost all of our observation work is conducted. The largest, oldest females would be the rarest animals in an already rare species. They would roam thousands of miles of open water and surface near a research boat essentially never. A shark like that could live a 50-year life and never once drift within visual range of a research vessel. We did not fail to find her because she was hiding. We failed because we were not looking in her part of the ocean. If you want a sense of what an animal like that might actually look like, consider deep blue. Deep blue is real, the largest great white ever reliably filmed. A female estimated at around 20 feet in length and roughly 4,500 pounds. Captured on camera off Guadalupe Island, Mexico, believed to be approximately 50 years old at the time. In the footage, she makes a research cage look like a child's toy. She dwarfs the divers filming her from inside it. Her girth alone suggests an animal that has spent decades growing uninterrupted in deep, open water, far from human observation. And to be completely clear, there is no evidence connecting deep blue to what happened to Alpha. Different oceans, different animals, no link has ever been established. She is mentioned here for one reason only, to demonstrate that great whites genuinely reach that size. The predator that consumed Alpha was not a creature from mythology. It was a shark, an ordinary shark of extraordinary dimensions doing an ordinary shark thing. Somehow that is worse. Now here's what almost nobody's talking about, because the Alpha story is compelling enough on its own that most people stop there. A giant great white eating another great white whole. That sentence alone is enough to make someone reconsider every decision that ever put them near open water. Entirely fair. But the headline is the least disturbing part of what the data revealed, because once researchers accepted what happened to Alpha, they went back through the existing record hunting for patterns they had previously dismissed, and what they found extends far beyond one morning off the coast of Australia. Great white predation on great whites is not a freak accident. It is not a 1 in a million collision of two animals in the wrong place at the wrong time. It is a documented behavior, and the evidence has been sitting in the record for years. Marine biologists have long known that great whites are cannibalistic. Larger individuals dominate smaller ones at feeding sites. Juveniles are genuinely at risk from adults sharing their water. The behavior begins before birth. Developing pups consume their unhatched siblings in the womb, a reproductive strategy so well established it has its own terminology in the scientific literature. Dead great whites have been recovered bearing massive bite wounds with arc spacing and serration patterns that could only have come from the jaws of another great white. And it is not only the dead ones. Researchers and divers have photographed living great whites carrying old healed-over scars in that same unmistakable pattern. Sharks that were bitten by one of their own and somehow survived. Every one of those scars is a story that happened out of sight. And it gets stranger still. In 2024, researchers published a study in the journal Frontiers in Marine Science describing what they called the first documented predation event on a porbeagle shark anywhere in the world. A pregnant female porbeagle had been fitted with a satellite tag by a team from Arizona State University. The data from that tag showed she had been attacked and consumed by a large predator. The temperature and depth profile recorded by her tag bore a striking resemblance to what Alpha's tag had recorded years earlier off Australia. The great white was listed as the primary suspect. The data signature was almost identical. Woe, incidents, 2 oceans, 2 different shark species being consumed by a predator whose tag signature science now recognizes. The lesson keeps repeating. Being a large, dangerous shark does not place you safely at the top of the food chain. It just means that whatever eats you has to be larger and more dangerous. But the single most dramatic development in this entire story did not happen in 2003. It is happening right now, and it has completely rewritten what the word apex predator means. Off the coast of South Africa, something has shifted in the relationship between great whites and orcas. Not the way it shifted for Alpha, in the dark and unreported. This time, on camera, in daylight, in front of boats full of researchers and tourists. 2 male orcas operating off the southwestern coast of South Africa, nicknamed Port and Starboard by the researchers who study them, began hunting and killing great white sharks with a level of surgical precision that stunned the scientific community. They would locate a great white, flip it onto its back to induce tonic immobility, hold it there, and then tear open the body cavity with devastating accuracy and extract a single organ. The liver, every time. A great white's liver is enormous. It can account for nearly a quarter of the shark's total body weight. It is massively calorie dense, packed with a compound called squalene that makes it more energy rich than almost any other tissue in the marine food chain. Port and Starboard learned to read the anatomy and hit it with the precision of something that had studied the problem. They would take the liver and leave most of the rest of the carcass intact on the beach. Scientists standing on shore would sometimes smell the kill before they saw it, the distinctive oily smell of shark liver drifting across the water in a slick. That was documented in aerial footage in 2022. The scientific community was already stunned. Then, in 2024, a study published in the African Journal of Marine Science described what happened in June 2023 off Mossel Bay. Starboard, one of the pair, was observed hunting and killing a 2.5-meter great white shark entirely alone, without his partner, and completing the entire process in under 2 minutes. He gripped the shark's left pectoral fin, thrust forward with it several times, eviscerated it, extracted the liver, and was later photographed from the research vessel with a bloody piece of liver in his mouth. The entire event took less time than it takes to read this paragraph. Then in January 2025, a study published in Ecology and Evolution confirmed what many researchers had suspected but not yet proven. A 4.5-meter great white shark carcass had washed ashore in southeastern Australia in October 2023. Its liver, digestive organs, and reproductive organs were missing. 4 distinctive bite wounds were present. Genomic analyses performed on swabs taken from those wounds confirmed the presence of killer whale DNA in the major bite area. The first confirmed genetic evidence of killer whale predation on a white shark in Australian waters. The same country where Alpha disappeared in 2003. What this means is not just that orcas can kill great whites. That was already known. What it means is that in certain parts of the ocean, great whites have stopped being the apex predator and started being the prey. And when that happens, the ecological consequences are immediate and severe. Great white sharks have largely abandoned South Africa's southwestern coast in recent years. After Starboard's June 2023 kill alone, the great whites left that area for approximately 4 months, then returned in smaller numbers. When great whites disappear from a region, the animals they normally control, the seals, the smaller sharks, the fish populations, begin to expand unchecked. A 2025 study from the University of Miami Rosenstiel School of Marine Science documented exactly this, finding that the disappearance of great whites from False Bay over more than 2 decades had led to a documented increase in Cape Fur seals and 7-gill sharks, with associated declines in the smaller fish and shark species those animals prey on. The removal of one apex predator from one area had rippled through the food chain in ways that researchers are still trying to fully map. The picture that has assembled itself from all of this, from Alpha's tag washing up on a beach in 2003 to the confirmed genetic evidence of orca predation in Australia in 2025, is of an ocean that is more complex and more dynamic than any model we built to describe it. The food chain everyone assembled in their heads, great white at the top and everything else arranged neatly beneath, is not accurate. It has never been fully accurate. The great white sits at the top in most contexts, against most animals in most conditions, but the largest great whites prey on smaller great whites. Orcas in certain regions have learned to kill great whites with remarkable efficiency. And somewhere out there, as Alpha's tag proved, there are individual great whites of a size that most of our models and most of our tagging programs have never directly measured, doing things to other apex predators that we only learn about secondhand when a data logger drifts ashore on a beach. We never named her, the predator, the one that consumed Alpha. She has no designation, no record, no photograph attached to her existence. She moved through those waters off southwestern Australia, did the single most remarkable thing science has ever inferred about her species, and vanished back into the deep without once being seen. She may still be out there. There is no reason to think she is not. If she was the size the data suggests, and if she was already mature in 2003, she could be in her 50s or 60s now, still roaming whatever deep water she calls home, still occupying a position in the food chain that our models did not account for and our boats cannot reach. We have tagged a few dozen individual great whites and drawn confident conclusions about an entire species. We have studied mostly the younger, smaller individuals that come close to shore and called that the whole picture. We have built population models and conservation strategies on data that systematically misses the largest, oldest, most ecologically significant animals, because those animals live far out in open water, where the research boats are not. Alpha's tag drifting ashore 4 months after her disappearance was a message from the deep. It said, in effect, something is down here that you did not account for, something larger than you believed possible, something that treats your apex predators as prey and descends nearly 2,000 feet to digest the meal in private. Consider the full weight of what that means for everything we think we understand about the ocean. The Pacific alone covers roughly 60 million square miles. All the world's oceans combined reach past 100 million square miles, of which we have meaningfully explored only a fraction. The deep open ocean, everything below roughly 1,000 feet, is for all practical purposes invisible to us. Whatever happens down there happens without our knowledge, without our cameras, without our instruments. We are drawing confident conclusions about the ocean from a sample so thin it would embarrass any statistician. We tag a few dozen sharks and call it a population study. We watch the coastlines and call it an understanding of the species. We measure the animals that come to us and assume the ones that do not come to us are the same size. They are not the same size. Alpha's tag proved it. The genetics in the Australian carcass confirmed it. The footage of Starboard carrying a liver in his mouth made it undeniable. The ocean has levels we have not reached, and residents we have not named, and dynamics we have not accounted for in any model that currently guides conservation or policy, or our understanding of what lives in the water beneath us. Somewhere out there right now, another recorder is attached to another animal, quietly logging the next thing we are not supposed to know. When it washes ashore, I will be here to tell you what it found. Subscribe so you are here when it does, because the ocean is not finished surprising us, and I think we're only beginning to understand what is actually in the water.